Oh, once more, 1 second. Yeah, okay, fine. Yeah, sorry for that. So in the last session, we discussed about the LCD screens and sensors like the temperature and HCSR04 sensor. And we also had a small DIY task, and I hope you guys were able to do that. I hope you guys were able to do the task. And yeah, and like if you are facing any issues with the DIY task, let us know in the WhatsApp group. We'll help you in whatever way we can. Yeah, and so moving on to today's session. Today we will be discussing about IoT. Like IoT is introduction of things in Internet of Things, and like a basic intro to IoT. Then we will move on to some communication protocols like UART, SPI, and I2c. Okay, and for the SPI, we'll just do a Tinkercad demo, and like for I2c, you'll be coding along with us. So this is what we have planned for today. And yeah, so moving on to IoT. So what is IoT? IoT is basically in the full form is Internet of Things. What IoT basically means is there is a system of things or gadgets that are able to collect and exchange data. So, for example, you have your voice assistants like Google Assistant or like Alexa, for example. Like suppose you want to turn on your light with Alexa, so you can just using your voice, you can communicate with Alexa, and Alexa will also be connected to your home appliances. And because of this connection, you will be able to do your tasks more easily. And like the main aim of this IoT uh, industry is to automate tasks and make consumer life more and more easier. So this is what IoT basically means. And like moving on, we have yeah. So this is what I told earlier. Like this meme is a really good way to demonstrate what IoT does. So if you don't have IoT, like if you want to turn on light, you'll have to go to the switchboard, turn on light, turn on the light. But for example, if you have a smart home, you will can do that same task just sitting on your chair. Like the effort required to do stuff is like very minimal. This is the main advantage of IoT. Okay, so I hope this is clear for you guys. So now on the next slide. Now, what are the main components of IoT? Like while communication, how do we actually do this? So we will have some devices which are connected. For example, if you remember in the last session, we used a temperature sensor. So how did we do that actually? So we used a temperature sensor and a microcontroller. So these were the two devices in that IoT system, and these two devices were communicating with each other and transmitting data. And that was like this is the small scale version of an IoT device. And devices should be interconnected. In the temperature sensor case, the devices were wired, whereas, for example, in the Alexa example case, the devices were wirelessly connected. So you can have either wired or wireless, depending on the mode of communication. Also, on large scale IoT devices, the data processing and storage is a very important thing. Like in the small scale examples, like the temperature sensor, data storage is not that big of an issue. But when the IoT systems become more and more complex, you can have data storage becomes more important. And for storage, like usually the preferred way is cloud computing. Like an example of cloud computing would be the Google Drive, which all of us use. And the last part in IoT is user interface. The while designing the UI. Like for any IoT system, the main aim should be minimum effort for the user. Like it should be easy to understand so that the user has an incentive to use it again and again. So this is the main things which points and which I wanted to talk about IoT. So I hope you guys were able to follow along with me. And yeah, so if you have any doubts, you can put in the chat. So moving on, yeah. So one more slide is there, like applications of IoT. Like as I said earlier, we can make smart homes, and on an even larger scale, if we apply this, we can go think about smart cities as well. Also, this IoT technology is uh, also used in farming and like manufacturing industries also, where we need to automate tasks. So to do them more efficiently and to produce things on a larger scale, IoT is a really good technology. Also, in medical and healthcare industries also, this IoT can be used because, like for example, nowadays technology has evolved so much that robots can fully do surgeries by themselves. So this is how powerful the IoT technology is becoming, and it's still a really up and coming industry. So it's quite interesting to see how IoT technology will go into the future. So yeah, that's basically about IoT. And now, as I said earlier, in IoT, the devices need to communicate with each other. So now we'll see how devices actually communicate with each other and like what are the different ways through which the devices communicate. So the first communication protocol or method is UART. Like, and this is one of the more oldest and most widely used communication protocols. UART stands for Universal Asynchronous Receiver and Transmitter. So, what does the word asynchronous mean? This is important. Like, so asynchronous means there is no clock pulse to which synchronizes data transmission between devices. And I will, in the next slide, I will talk about what clock pulse means. So, for now, just remember that in an asynchronous communication, there is no clock pulse. Also, this is a character-oriented protocol. That is, each data is transmitted bit by bit. Say, for example, you have a data with 0, 1, 0. So how do the two devices communicate this data? So the first device will first send the bit 0, it will get received by the second device. Then it will send the next bit 1, and then it will send bit 0. So this is what is meant by transmitting data bit by bit. I hope you got the point. And another feature of UART is it is a peer-to-peer network topology. So what peer-to-peer means is basically at a time two devices talk to each other. Like peer-to-peer in like English terms, uh, you can say like talking with your friend. This is kind of similar to that. And also in UART communication, it's the pin connections are very easy. Like you only have 3 pins, which are TX, RX, and ground. And I'll explain what this means in a few minutes. So this is just the small intro to UART, which I wanted to tell. And yeah, so moving on. Okay, now clock pulse. I told earlier that UART is asynchronous, and asynchronous means there is no clock pulse. So now I'll show you what a clock pulse actually is. So as you can see in the diagram, there is a signal. It oscillates between low and high states like this. So a clock signal is basically a signal that oscillates between high and low, as shown in the diagram. And the main use of this clock pulse is to synchronize the data. Like whenever data is transmitted by one device, at the same time the data should be received by the other device. That is the main use case of the clock pulse. And there are different ways of different types of clock pulses. For example, you can have edge triggered or level triggered clock pulses, and I'll explain this in the next slide. So here you can see on the topmost diagram you have a positive edge triggered clock pulse. So what does this mean? So if you look closely in the diagram, the data changes only when during those times when the clock signal moves from a low state to a high state, like, and that's what the dotted lines represent in the first diagram. So only during those instances of time the data can change. The data may or may not change at this point, but the main point here is that if the data is supposed to change from like high to low, something like that, it can only happen during those instances. And using the same logic, if you go for a negative edge triggering, data changes during a high state to low state uh, transition. Okay, and one more type of clock pulse is there, which is level triggering. In this case, data gets transmitted only when the clock pulse is high. If it's a high level triggering, then you will have the case which is on the bottom left. And if you have a low level triggering, you will have the case which is on the bottom right, which is data will be transmitted only when the clock pulse is at a low state. So I hope you guys understood what clock pulse means. And yeah, so that's basically clock pulse. And now I will show you the connections in UART. So if you look at this diagram, you have an Arduino Uno, and I told you earlier that there are three pins, TX, RX, and ground. So if you look at the bottom right pins of the Arduino, you can see pins marked TXT, RXT. So for if you want to have UART communication between two Arduinos, these will be the pins which you use, the TX and the RX in the bottom right. And on the top right, you can see the same thing. And while connecting the two devices, the TX of one device must be connected to the RX of the other device. And similarly, for the second blue line as well. And on the red line, only the device 1 can like transmit data to device 2, and on the blue line the device 2 can transmit data to device 1, and the black bar is basically the common ground for both the microcontrollers. And yeah, on the bottom picture you can see the data transmission, which is bit by bit. This is what I talked about earlier. So yeah, so like moving on, the communication in UART. So it depends. So this is a general block diagram of how UART works. And so when UART starts, the data line first goes from a high to low state, and it stays there for a specific period of time. So can anyone tell how much that specific period of time must be? Like, if you have any idea, just put it in the comments. Like, the what I'm asking is like, for you can see in the diagram some small blocks. So like, how much does should each block of time should be? This has something to do with baud rate, and baud rate is something which we studied in the first session. So yeah, okay, somewhat in the nanosecond range. That's okay, but I I would like you guys to think this in terms of the baud rate, if you can. Mm. Yeah, okay, fine. So I'll just give a small recap of baud rate. So baud rate is basically the rate at which data is transmitted between devices. So suppose you have a baud rate of 9600. So that means in 1 second, 9600 data bits can be transmitted. So if we go by that logic, each data bit will take 1 by whatever the baud rate is. So that was what I was hoping for. So anyways, okay. So initially the data line goes from high to low, so that to show that the data transmission is being has begun. And yeah, after it starts the data communication, it will start sending the data. Now the data bit can either be 5 to 9. Now this basically depends on the UART application or the device which you are transmitting. It can be anywhere between 5 to 9, but it cannot be more than 9. Like that's one problem with this UART communication. And also there is an optional parity bit at the end. So why do we need this parity bit? So the reason for this parity bit is, uh, say, uh, as I said, UART is asynchronous. So there is no clock pulse to synchronize the data transmission between devices. So in case the transmission between devices is not happening at the same time, the parity bit will show an error, which basically means your device has a fault and you will have to fix it. So that's why we have a parity bit over there. Also, at the end, you will have a stop bit. In older devices, like when the technology was not so advanced, you had two stop bits. So, but nowadays, with one stop bit itself, the device will be able to the recognize that the data transmission has stopped. So this is how the UART data packets are arranged. And okay, so one last thing about this data transmission is there are three main modes of transmission. One is this simplex mode. In this simplex mode, simplex, half duplex and full duplex, and like simplex mode, as you can read, sender can send data and receiver can receive data. So that's it. Like sender cannot receive data. That's the main disadvantage in the simplex mode. While in the half duplex, sender can send data and receive data, but it can't do both of them simultaneously. But full duplex can overcomes all of these problems, like sender and receiver can send and receive data simultaneously. So, and in UART communication, it depends. If you, it depends actually on the device. It can be simplex, half duplex, or full duplex type of communication. And the one major problem with this UART communication is that it's peer-to-peer. Like at a time, only two devices will communicate with each other. Like you can't communicate with multiple devices using UART. That's the main drawback. And now let's see how we can overcome this drawback using another mode of communication called SPI. So SPI stands for Serial Peripheral Interface. And here we overcome the major drawback of UART, that here you can communicate with multiple devices at the same time. Also, one key difference between UART and SPI is that in SPI communication is synchronous. Like there will be a clock pulse which synchronizes all of the data transmission. Also, this is a master slave type. So what master slave means is like there will be one master controlling some other devices. One master device will send data to its slave devices, and it can be multiple slaves. But there is one problem which I'll talk about in the upcoming slides. Also, compared to UART, SPI is a full duplex mode of communication. Like in UART, you can have all three, but in SPI, it's only full duplex. And yeah, so in SPA, the pin connections are slightly more complex compared to UART. So you have four main pins, which are MISO, MOSI, clock pulse, and the chip select, or slave select, or enable line, whatever you want to call it. So yeah, so now I will show you how SPA communication works. Yeah, so in the Arduino diagram, as you can see, over here, these are the four lines which we usually use if you are using a Arduino Uno, the SPI, MISO, MOSI, CK and SS. So, okay, now I'll explain what these lines actually mean. So, the red line, which is MOSI. MOSI basically means master output, slave input. And as the name suggests, master output is basically when the master wants to send data to the slaves. And similarly, the yellow line, MISO, the master inputs data and the slave sends data. So this is a simple definition for MOSI and MISO. CLK line, as I told earlier, would be the clock pulse which synchronizes all data transmission between devices. Also, you have the chip select lines. Now let's understand the chip select lines. So what chip select lines are basically, suppose your master wants to talk to a particular slave, say the rightmost slave, which I will call, which has the chip select line CS2, the orange one at the bottom, if you can see it, this one, this orange line. Suppose master wants to communicate this slave. So what it does is, for this slave, the shift select or the slave select line will go to a low state, and for all others it will remain high. And what this basically does is, whenever the chip select lines are high, there is no communication between the master and that particular slave. That is the main function of this chip select line. Do you guys understand this connection diagram over here? So if you have any doubts, you can ask in the chat. Yeah. So okay. So this is the data transmission in SPA. So first of all, as I told, yeah, okay. Now I want to ask one question. If you see the SCK line, what kind of clock signal is this? So if you know the answer, you can just put in the chat. Yeah, nice. So it's yeah, it's positive edge triggering basically. So like if you have any confusions, you can see the arrow and the dotted lines. This that might help you. And like one more thing which I want to say is, like, if you see the MOSI line at the first positive edge, the data doesn't change. So like it's not compulsory that the data must change at a particular positive edge. So this is one thing which I missed out earlier. Sorry. Yeah. So here, whenever first of all, whenever the serial clock has a positive edge, the data gets transmitted. Also at the bottom, you can see the slave select line. The slave select and the chip select are the same line itself. This is just a different way of saying it. And you can see that it's low the entire time. the entire time the data transmission happens, this slave select line is low. So that low basically means that the master and slave are actively communicating with each other. So the master first sends an output through the MOSI line over here. After that, the slave sends a message back to the master. And after this communication happens, the slave select line again goes back to high because the data transmission is basically over. So this is SPI communication. But one major drawback of this whole SPI thing is that you cannot connect infinitely many devices because like there is a restriction on the number of pins that is there in this master device. So you can only connect as many devices uh, as there are in the number of pins as the number of pins in the master pin. So this is one problem, but this is definitely improvement compared to UART. Yeah, okay. So now I'll just show you one SPI demo on Tinkercad. So if you go here, yeah, so opportunities. Yeah, so you guys can go to go through this link. Yeah, so you can take 2 minutes to go to this website. Like, please go to this website. So I'll show you a demo of SPA over here. Oh, okay, fine. Can you just give me 1 minute? Yeah, so is this working? If it's working, just type yes in the chat. Yeah, good. So yeah, so just take 1 minute to join the website, please. Yeah, so I hope everybody has joined the website. So if you have any if you still have any difficulties, just let us know in the chat. So yeah, moving on. Yeah, so in this website, 1 second. Yeah, so okay. Yeah, so this is basically SPA simulation, and if you press start simulation over here, first of all, you can see that there are 4 LEDs over here, and one LED is continuously blinking. So can you guys say, guess what the LED basically represents? Like we discussed that there will be 4 pins in the SPI. So which pin will that LED represent? So any guesses? Yeah, nice. So it represents the clock pulse, because I said that earlier, like the clock pulse will continuously change from high to low, and that's why the LED is basically blinking. And to the right of the clock pulse, you have a yellow LED, and this LED is staying high all the time. So can you guess what that LED might represent? Yeah, nice, Adharva. So it basically represents the slave select line, because right now there is no communication going on. That's why the slave select line is high. Now, say I press a button, or like let's say 5 over here, can see that the slave select line goes low. That means the data communication has started. Then the blue line went high, and then the red line. So with that output, can you guess what the blue represents and the red represents? The blue LED glowed first, and the red LED glowed next. So what is the significance? Can you, any ideas? Like those will be either MSI or MISO. So can you guess which one is which? Okay, so which one is the blue line? Blue LED. Is it the MSI or MISO? So, yeah, good. So the blue, since the blue LED glow first, it represents the MSI. So as you can see over here, this one is basically our master, because it first recognizes whatever button we pressed over here, and first after this master recognize which button is actually been pressed, it will transmit this data, and then the slave will recognize, get the data, and it will display it over here. So that's basically how the SPA works. And say, so, and the reason why blue is MOSI is because first the master transmits this data to the slave, and then on the red light, what happens is the slave just sends a data bit saying that, okay, your message has reached here. That's what the red light represents. So now if you click on 8, any button of your choice, you can again see first the blue light glows, uh, yeah, and then the red light, and yeah, and so the data is here. So this is one small demonstration of SPA which I want to show. And if you see earlier, here we have connected the same 4 pins which I showed over here. Yeah, so yeah, so over here you can see these 4 pins for SPI which we usually use, the serial clock, the MIS, MOS, and SS. So the same 4 pins are shown over here also as well. So yeah, this is basically SPI, and this is a nice demo of how SPI actually works. Now you might be thinking why we actually use two Arduinos here. So I can explain that also as well. Here, if you see, you have a limited number of digital input output pins. Like you used so many digital input output pins over here for this keypad over here that you don't have any digital input output pins for the LCD screen. So in this case, if we actually wanted to display whatever the number we pressed over here, we need more digital input output pins. And since we don't have enough pins over here, we use two Arduinos and the SPI communication. So this is one nice application of how SPI is actually used in the real world. So that's basically about SPI, and I hope you guys understood UART and SPI. So now you can take a small 3-minute break, 3 or 5 minute break, and Mayur will start with I2c in a few minutes. Yeah. And if you have any doubts, you can put it in the chat right now. We'll be clearing them as soon as possible. Oh, okay. So, like, which part do you want me to repeat? Like, can you just tell in the chat? Okay. So that part also. So, suppose you wanted to do this project on one Arduino, it won't be doable. So, and I'll tell you why it's not doable. Say you have this keypad over here. You can see it has so many pins. Like, let's count it actually. 1, 2, 3, 4. You used 8 pins just for this keypad. Now for the LCD, if you come over here, you again use some 1, 2, some 6 pins, I guess, 6 or 7 pins. So you don't have that many pins over here, if you can see properly. And like you can't use these 2 pins because this is mainly used only for UART communication. So you have say 2 to 13 at the max. So you don't have enough pins to connect both this keypad and the LCD screen to the Arduino to one Arduino. So in these situations, it is best if you connect one keypad to one Arduino, one the LCD to other Arduino, and you can use SPI communication to transfer data between these two Arduinos. So I hope you got my point. And if you have any doubts, further doubts, you can put in the chat. We'll be explaining them. And yeah, so you can take a short break, and Mayur will be continuing with I2c now. Thank you.
Yeah, hi, good morning, guys. Is my screen visible? Put yes in chat if it is visible. Yeah, fine. So, hi, myself Mayur, and I'm first year undergraduate from Department of Metallurgical and Materials Engineering. So, further, I have actually talked the basics about the two communication protocols, the Spi Communication Protocol and UART Communication Protocol, and have and like uh, he has covered many basic concepts like the serial clock, the synchronization, and all. So I2c protocol is actually a blend of both SPI protocol and UART protocols. So what I2c actually stands for? So I2c is inter-integrated circuit. And this is also known as two-line interface because this is actually a channel where multiple masters and slave communicate with each other. Unlike SPI, only one master can communicate with multiple slaves. But I2C with I2C we can control multiple slaves with multiple masters. So it is known as I2c bus. So this communication protocol was originally designed by Philips Semiconductor in 1982, and this protocol can communicate data among multiple masters and slave integrated circuits. So moving on. So as said earlier, it has two lines for data exchange. One is SDA line, which is serial data line, and one is SCL line, which is serial clock line. So yeah, so over the master always controls the SCL line. It is always on, and like slave can exchange data from like in SDA through SDA, master can send data to slave, and also slave can send data to master. So SCL is serial clock pin that synchronizes data, and SDA is serial pin that sends or receive data. So moving on further. Uh, so as said earlier, a single master and the I2c protocol can do both serial master, multiple slaves and single master, and multiple masters, multiple slaves. So actually, master doesn't have any address. This also I2c protocol, like it can communicate only one master and one slave at a time. So can you guess what type of protocol it is like? Like, is it duplex or like what type of mode? Any idea? Only one master can communicate with one slave at a time. Yeah, right. You guessed right it. You guessed it right. It is half duplex mode. So actually, every slave is assigned a particular address by a particular address, and this addressing is done by a process which known as addressing, which I will be discussing further. So each slave has its own unique address. So in uh, uh, generally address is a seven address is a 7-bit long, or it can also be 10-bit long, depend upon what kind of IC you use as master. And with a 7-bit address, you can control 128 unique address, unique slaves. That is 2 power 7. Sorry, this is not 27. It is 2 power 7. And with 10 bit, you can do 1024. That is 2 power 10 slaves. And to connect multiple slaves to a single master, and we should wire them like this. Pull up and pull down register. Pull up registers. And also when now, since it is a duplex mode of communication, if two masters are like trying to communicate with a single slave at a time, so there is a mechanism which detects whether the bus, this is called the I2c bus, this is common to all the, like, this is SDA line and this is SCL line, and when one is communicating with other and other wants to, suppose master 1 wants to communicate with slave 1 and master 2 also wants to communicate with slave 1, and if master 1 is already communicating with slave 1, then master 2 will check whether the serial data line is like free or not, like is it transmitting some data or not. If it is transmitting, then it will hold on, and after this is like after this bus is freed, it can send its data to slave 1. So yeah, that's what this slide covers. And now we will take a typical example of transmission of data from a master to slave. Like how does it happen? So this happens in terms, there are like 5 stages of transfer, and this 5 stages of transfer is completely can be known as message. So there is a start condition which initializes the communication, and then this is the address frame, like this is the process of addressing which I was telling before, and this is read or write bit which I will be discussing. This is acknowledgement or not acknowledgement bit. This is data bit, like it can share only 1 byte of data at a time, not more than that. And this is stop condition to complete like to stop the transmission of data between the master and slave. So start in what happens during start condition? The SDA line goes high to low before SCL line goes high to low. So with this, it can be concluded that the bus is ready for transfer of data. Now what happens is the master after start condition, master sends a 7 or 10 bit address in the I2c bus, and each slave receives that, and each slave compares with their respective addresses, and if the address matches with the address frame, then it sends a ACK bit to master back. Like it is like giving a thumbs up that I have received the address you sent matched with me, and I am ready for communication with you. It is like yeah, so it sends a ACK bit to the master, and after address frame, as I showed, it has a read or write bit. So it signifies that if that bit is low, then it signifies that master wants to send data to slave, or vice versa. If it is high, then master is requesting data from slave. So what actually was NAC and ACK bit? This is actually a thumbs up from one who is receiving data. Let it be master receiving data from slave or slave receiving data from master. It is like giving a thumbs up that I'm ready for communication, or it is a thumbs up for that I have received data successfully. And the data frame, like after master detects the ACK bit after addressing, after detection of address, the slave frame is ready. The first data frame is ready to be sent. Like the data from, since we are taking the case of transmission of data from master to slave, the master is ready to send the 8-bit information or data to slave. So this is always 8-bit long, and it is sent with the most significant bit first. And after when this data frame is received by slave, it again gives a thumbs up by ACK or ACK bit. If it doesn't receive, then it gives it gives a NACK bit. NACK bit is like it leaves the SDA line high, and ACK bit is like it generates a low pulse. And yeah, so ACK bit must be received either. Yeah, okay. So after stop condition, after this, we have like done with data transfer, and we have to like stop the communication between that master and slave, and we have to end the transmission. Like we have to like empty the bus for further communication. So after all data frames are communicated to vacate bus, the SDA line goes high. After SCL line goes low to high. So what actually happens is like when the SDA line is high, it signifies that the bus is like free, and it can like anyone can start communication between any communication can be started between master and slave. But when it is pulled by a master low, it means that the communication uh, is being taking place between the master and a particular slave to which address is received. So this is semantic of what I told in last few points. So this first point, the SDA line goes this is the start condition which we discussed, and after the start condition, the master sends this 7-bit address with a read or write bit at end, and after this so here the address allotted to this slave matches. So this is like it is like it has received it matches, and after this it sends a low pulse, giving a thumbs up to master that I have received your address and I'm ready to communicate with you. And after that, a data transmission of 1 byte from master to slave occurs. Again, after this the successful acknowledgement takes place because slave have received the data frame successfully. And after this, to end transmission, the stop condition is inculcated. So now there is a similar mechanism for a slave to send data to master with some extra, like it has some extra steps. So you can find it in the link here. You can get more information about I2c in the link here. So these in these 3 pictures, these are actually you would have you have done this
Yeah,
LCD.
can you just copy that link in the chat so that they can look?
Okay. It is like just for further reading. Oh, it is not good. I'll send it later. Okay, like it is like just for further reading.
Okay, fine.
It is not getting copied actually. Yeah, so these 3 pictures, like of this, you are familiar with this, and you know that you use some 7 or 8 pins at a time to connect it with to display something on this LCD screen using an Arduino. So this is this black PCB. You see that is that is a I2c module for LCD. Like these pins
And
are like connected here.
yeah, Mayur, like you can go a bit slower, like slightly slower.
Yeah, sure, fine.
Okay, fine. Nice.
Yeah, so this this is connected, like these all pins are connected to this array of pins, and this circuit here, oh, see this circuit over here manipulate like does some internal it has a IC fitted here, you can see here, and like this IC will be communicating with the Arduino with these pins. You can see SDA, SCL pins here. Also, we'll discuss this in a project further. So, like it reduces a number of pins with these modules, like OLED display, which has like this many pins. You can see this. That like there are many pins here. It is actually blur, but it has many pins here. And with the I2c, like with a module, it can be just compressed to 4 pins, reducing the number of like the complexity of circuiting, like circuiting it or interfacing it with the Arduino, and these are like okay, so these are like control with many libraries. Like there is Adafruit underscore liquid crystal.h library for this I2c module with LCD, and this is like 0.567 segment LED, which is again I2c, which is again dependent on I2c. You can see here like this is clock pin and this is data pin, and it has again this has 4 pins. Again, I'll show that each LCD 7 segment display has like 10 pinouts. So see, you can like 40, like 10 pinouts. They are just compressed to 4 pinouts with I2c module. So yeah, moving on further. So now coming to advantages and disadvantages. So the advantage of this communication protocol is it reduces the circuit complexity, like because it has just 2 wires and 2 wires. I mean, there is also one common ground wire which is like base condition for all the high and low. The condition that go like the going of the SDA line from high to low and SCL line from high to low. Like this is all like this all has a base ground, and so these have actually 3 wires. One is SDA, one is SCL, and a common ground. So and it supports multiple master and multiple slave, unlike SPI. And NACK it also like has like the backup for like the data is being received successfully or not, and hardware is less complicated than with UARTs and widely used protocol. Disadvantages is it has lower data transfer rate than SPI. Now with SPI, like we can control like SPI, like we can do the data transfer and receiving like simultaneously, but there is no such like thing in I2c. So it has a bit slower data transfer rate than SPI, and it is like it has some common it has a common bus rate, so it is like a bit slower than other protocols, and the size of data frame is limited to 8 bits, and as compared to SPI, you need some more complicated hardware. So these are some of the advantages and disadvantages. Now, where are these SD and SCL line located on Arduino? So these 2 pins over here after this AREF are I2C. This is SCL and this is SDL line, and also the analog pin A4 is SDA and analog pin A5 is also is SCL. So like these have these are like internally connected. Like it is fine if you start communication with the 2 pins here or over here. Like it has no problem. So yeah. So Now, while coding it with Tinkercad, in Tinkercad, we will need this library #include wire.h library to start to communicate between master and slave with I2c communication protocol. So this library actually enables the inbuilt pull up and pull up registers of the Arduino Uno. So we don't need to connect it by ourselves. Like you would have seen in the slides before that there were two registers connected. So this by, by including this library, the Arduino set the inbuilt pull up registers in it. And yeah, so these are some of the functions of it. Wire.begin transmission, wire.end transmission. I'll discuss them a bit in detail, in a bit detail. So wire.begin. So this initiates the I2c communication, and wire.begin, like you have to pass an argument in wire.begin with the slave address, and you don't need to you should not pass argument in wire.begin because for master code, because master is one which has no address but slave has an address. So wire.begin is like the condition you saw it over here. Wire.begin, this all. It starts the start condition and address detection. Like this is the condition with wire.begin. And now like wire.begin transmission to a particular address. So after this, with this function, we can transmit the data, like to transmit, we can like start the data transmission after this. Then we can write to the SDA line the data or read from the SDA line depending upon what function we want to execute. And wire.end transmission, it will like stop the transmission, like it will terminate and like drain out the I2c bus, like for further communication. It will pull SDA pin high and SDA line high. And wire.read is same, like if you want to write to SDA pin from, suppose you want to send some data from master to slave, then you should like write in the master code that wire.write and the data you want to send, and in slave you would write wire.receive, and vice versa when it is reversed. Like, and wire.request from address and quantity. Now when you want data from slave, you should request data from the master should request data from slave. So it will be this will be the address of slave from which it is requesting data and the quantity of data it is requesting. And this is wire.onReceive. This is the function which executes a function, like after it receives, then this function is executed. We'll see it in more detail in the code further. Now, this was the topic which was left yesterday, and today we will be using this in one of the projects. So I'll quickly go through this. So servo motor is just a motor which control whose angle of rotation we can control by ourselves. So it uses PWM, and because it is more efficient here with PWM, and these are some of the the functions of servo motor. Servo.name, like it initializes servo object for the connected servo. Then the name of your servo you have wrote here, dot attach means the pin number, like you can write like it initiates that, it says that we have attached the signal pin of servo to some of the PWM pins of Arduino. And servo.read, like if we want if we want to know that by what angle the servo has rotated, we will use this function, and servo.rate. If we want to rotate it by angle we desire, you will pass the argument here. Yeah, so now we'll simulate one of the projects here. So I request you to open Tinkercad for this. Have you followed till now, like the basic of communication protocol of I2c? Hello, are you following? Yeah, sure. Sure. So please open Tinkercad, and we'll do this small project. Now here what we are going to do is like we'll convert we'll control the angle of rotation of this servo motor with the potentiometer here, and this will be done by sending the data from potentiometer to servo motor here, and to demonstrate the data from master to slave, from slave to master, will send the reading of the servo motor back to master, which it will print on this I2c LCD. So, okay, so you can start coding along, build circuit along with me. I'll rotate this a bit. Need a I2c LCD. We'll need a potentiometer. We'll need a finally a servo motor. Yeah, so talking a bit about the pinouts of servo motor. This was the signal. This pin is for signal, which is to be connected to the PWM pin of Arduino, and this is power, which is connected to VCC or plus 5 volt, and this will be connected to ground. Let's say we'll connect it to PWM pin 11. And power pin to power pin, and the ground pin. Now I'll connect this wiper to pin A1, let's say, or connect it to pin A0. This I'll connect to this I'll connect to ground. This to VCC or plus 5 volts. And now, yeah. So this is important. Like now, I'll connect this I2c LCD, the SDA line, the which is yeah, SCL line to the SCL line of I2c LCD. SDA line to the SDA output. And VCC 2 plus 5 volts. And ground to qubit. Yeah, okay. So this is now one slave. This I2c LCD is slave for this master. I'll show it in code. And this now with this Arduino, this is a slave Arduino, and this is a slave I2c LCD, and I'll connect it with A4, like A4, which is SDA line, which I'll again give color blue, and the SCL clock line, which I'll give color orange as given here. And as said before, I have to like ground both the ground like for base condition of all the communication. Yeah, okay. So have you followed with the circuit till now? Put yes in chat if you have followed.
Yeah,
Yeah.
just the potentiometer connection. Can just explain.
Yeah, okay, potentiometer connection. This I have connected to ground. This another terminal to plus 5 volt, and this to this is to analog rate analog. Yeah, are you guys following? Any doubts in circuit? Yeah, so one connected with servo is master, is slave, and also the I2c LCD is also the slave, and the one which has one which we have connected potentiometer is your master. Yeah, so deciding which one is master and which one is slave, like it will be done in code. Like one with with just wire dot begin will be master, and one with wire dot begin and address will be slave. We'll come to it. You'll get it when what is master and what is slave during coding.
There is one doubt in chat.
So that's what I told it before. Like we have to set some baseline for, like you have seen that it goes some high, low, high, low. So like the baseline, since it is a bus, then the baseline for both the Arduinos must be same. So baseline, we are doing it ground. Okay, like if we have to like show that SDA line is going high to low while SCA line is going low to, before SCA line going low to high. So low to high, they are relative, right? So that must be a common for both these. So this, the grounds of both are connected so that this is common to, the ground is common to the I2c bus. And it is base for all the like the clock signal and base value. Base value means the low voltage value. I hope it is clear. Yeah, then shall I start coding? Yeah, okay. So I start coding now. First, I'll code this master Arduino. Uh, yeah, okay. So I'll include first the wire library for initializing I2c protocol. Hashtag include. I'll define a variable known as slave address. Let me give it 1. So we'll use this 1 here for communication between like if I use the 1 here, that the what address I declared there, then it will like start communication. Then like this will behave as slave and this will behave as master. Yeah, so after defining slave address, I'll set this pin mode, the analog pin to input pin, A0 pin, since we will be inputting of potentiometer to Arduino. And after pin mode, we'll do wire dot begin. That I am not giving any argument here, which means that it is in master mode. This Arduino is in master mode, and we'll also initialize serial monitor if we want, in case we want to print any values. Yeah, okay. So after this, I would declare two integers, int pot value, the potentiometer reading, and I will store it in I store it in this variable, and another variable int value to be sent later, because we are sending an angle. We'll send we'll write say angle. So yeah, so after this declaration of this two variables, will make pot value, the integer type pot value, int, sorry, pot value equal to analog read pin A0. Sorry. This will be this over this A0 will receive a number will receive a number from 0 to 1023. So we'll map this to this to will map angle variable with the potentiometer variable, angle equal to of pot value 0,1023 to 0,180. Okay, so yeah, so after this, we will do dot begin transmission to slave one, that is, I'll put the slave address to which it should transmit data, slave address, and which we have defined it here. So it will send, it will start communicating with the slave with address 1. So after this, while begin, I'll write to the SDA line wire dot write the angle value. End transmission with wire. Okay, so this is just a code for master to send value to send the mapped potentiometer value as an angle, as angle value to the slave Arduino. Now we'll code in slave Arduino. Here to will include hashtag wire.h. Then in void setup, also we have to include, we have to include servo.h, the library for Servo Motor. H. Include servo.h. Yeah. So again, I'll define same hashtag include if address hashtag defines slave address. Here. Now here I'll write wire dot begin and address. Now again I'm emphasizing the difference here is like I'm giving an argument here, which means that this is a master, this is a slave Arduino, because it wants this the master want to communicate with the slave Arduino with slave address 1 here. So it will like it is defined 1 and it will put that binary 1 into this, and this will received by this both this LCD I2c LCD and also this Arduino. And after this, since the bit it matches with this Arduino, it will give a thumbs up by acknowledgement that I'm ready for receiving data from you. So yeah, so that's important, like the passing argument to the wire.begin function is important for slave Arduino. Yeah, okay. So yeah, I'm also left with I have to define servo as an object. So with we will use this function servo into servo sr underscore 1. Let our servo name be sr underscore 1. Yeah. So after this, we'll use this function servo.attach dot attach attach, like we have named it sr underscore 1, right? So sr underscore 1. The name of PWM pin we have attached to it, which is 11, and we'll also begin serial monitor serial dot int serial dot begin baud rate 9600, and this is wire dot, this function is wire dot on receive event known as, let's say, receive event. We define this function here below. It is a void type function. Parameter int h. It's not that you should give name as a receive event only. You can give any other name. It is like just for simplicity of understanding code. Int h or any variable will work. And here I'll do wire dot read. So whatever data it is sent from this master Arduino to slave Arduino, this I'll store it in a variable which I will define it here. In angle equal to int angle. Let's don't initialize it. Then angle equal to wire dot read. Angle equal to wire dot read. Then after this, in void loop, we just write this underscore one dot write. Now this function will rotate the servo according to the parameter or the argument we pass to it. Here we want to rotate it by angle we received from I2c LCD. The I2c, the master. So we'll write what angle we receive to the servo motor. Yeah, and delay a bit. Yeah, so any doubt still now? Are you following with both the codes? The code for now is just sending the controlling the motor with the potentiometer. Further, we'll do code for controlling I2C2, where there will be multiple slaves. So are you following till here? You can ask any doubts if you have regarding coding. Those who didn't understand.
You can continue the code.
Yeah, please. Okay,
Uh,
please.
uh,
Slave
uh,
code. Okay, fine. So in slave code, we have included this library first for initializing I2C communication. Like it wants to do I2C communication. The slave want to do I2C communication. Then I have included this servo.h library for the functions of servo motor, and I converted the servo to the object, and uh, then int angle, I defined a variable angle in which I'll store the value that I get from this master. So to get that value, I should do wire.begin and put the slave address there. The slave address in the sense it is 1, and also in the master it was 1. So this master sends through SDL and the address of 1, address of this, like it is here for in this case it is 1. If you do it 2 here, then you have to do 2 also here. Okay, so also like it is not necessary that this should be same as this. It is not that. It is not that case. Only the binary, like it's the addressing should be done with the same binary code. So this will send 2 through SDA line. This will receive that, and again since I2C has that acknowledgement thing, so it will send back that acknowledgement message like we are not interested in it for now. And after that, this function does that. You're not, if you notice that you are not declaring the pin mode here, it is like declaring pin mode for servo motor. And I would like to initialize the serial monitor if I want to print something, and then this is wire.on receive event. Like when I receive something from Arduino, then whatever I receive should be stored in the variable angle. And in void loop, the servo should print or rotate the angle it received from the angle value it received from this master Arduino. Like, I hope the code is now clear. Any doubts, please ask again. I'll explain it again, no problem. This is important. Should I explain the master code again? Yeah, okay, fine. So go to master code. Yeah, so here also we have initialized with wire.h library, and then we have defined slave address as 2 because like you can define it here multiple slave addresses, but here we are like communicating with only one Arduino, so there is no problem here like defining only one. And this is the pot value, like potentiometer value, which I'll get from the analog read function, and I'll store the analog read of the potentiometer in this variable in here over here, like in this variable pot value, and I'll map this pot value to the angle I want to rotate the servo motor. The map function was discussed in the yesterday session while doing some, I think while doing temperature sensor. Map mean like linear map. If suppose you have x and y axis, so from 0 to 1023 to 0 to 180, you will connect a straight line, and like corresponding to some, suppose for 90 it will be 512 something. 512 will correspond to 90 degree, like that. And then I'll do wire.begin transmission to the slave address. This is like here I should tell like to what slave I should communicate with. So this will send the slave address to the I2c bus. After the slave address is sent in the I2c bus, this Arduino, the slave Arduino will match the slave address with the allotted slave address to it. If it matches, then it sends the ACK bit to the master back that I am like ready for transmission. I'm like ready for your any command. And with wire.write, with this wire.write, I'll send the data bit, the data frame to the master Arduino, to the slave Arduino. So, and after it is done, I'll free the bus for further communication. Oh, here I should give wire and transmission. I hope master code is also now clear. Yeah, can I move further? Okay, we'll once simulate this.
You can start the sim.
Yeah. See, the servo is rotating as we increase the potentiometer knob. I know why it is rotating slow, maybe due to connection. Yeah, like if you want, I'll print the values also. So here I'll print stop simulation. Real.println angle. Real.println angle, and in master Arduino 2, I'll print serial.println. Here I'll print servo.read sr underscore 1 dot read. Let's read. Yeah, so you can see that it is like rotated by 151 degrees right now. In it is showing one, and here also it is 151. And when I vary this, it is changing. I hope this transmission from master Arduino to slave Arduino is clear. Now moving on further. Now what I want to do with I2c is I want to send the reading of the servo motor, like the what angle it has rotated to this I2c LCD. Now for I2c LCD, since for I2c LCD in master code we have to include a library. Is like there are some functions, right? LCD.set cursor and all. Since we used to include a liquid crystal.h with a for simple LCD. Similarly for this kind of I2c LCD, we have to include a library known as include Adafruit underscore liquid crystal dot h, and now I'll define address for this Adafruit liquid crystal Adafruit underscore liquid crystal. I'll define the LCD name like same as what we did servo to sr underscore 1, converting it to object, and sr underscore related LCD, and define its address to be 0 or yeah. So after this, we'll set up the LCD by LCD dot begin, comma 2 dot begin 16, comma 2. Then I'll set the LCD cursor, LCD dot set cursor. These functions are same as what it were discussed yesterday, to 0, 0, that I mean here this coordinate, and then I'll declare to LCD to print LCD dot print. Let's say this. Now, since I want some value from slave, I'll use this function wire dot request from now I have to give here the slave address, which is 1, and the number of bytes I want to receive from slave, that is also 180 will fit in 1 byte. So I'll request 1 byte from slave and then slave, I'll write the slave code also. Then for now, they just yeah, okay. So we are done with slave, and you'll get this what I did it here after I write the after I modify the code in slave. So now I'll use a function named wire dot on request event. Request event, which will be declaring here as void any value, and request event. Here we don't need to add any slave address because it is already initialized there itself, and there itself mean the master Arduino. Now here what we will do is we'll write to wire dot write if code. Sorry, the servo reading sr underscore dot read. So yeah, so after this, I think I'm remaining with something. Yeah, okay. I'm remaining with printing it on LCD. Yeah. So I'll set the LCD cursor LCD dot set cursor to 0, 1, which I mean 0, 1. I mean by this coordinate over here, and LCD underscore 1 LCD 1 print LCD dot print angle and for degrees will print LCD, not LCD underscore dot we have defined it is that as LCD. We are accessing the ASCII value of the character degree from the ASCII table. Yeah, okay. So now I'll explain what actually I did. I'm requesting from slave 1 to I am requesting slave 1 to print to get 1 byte from to send 1 byte, and whatever it sends, I will store it in a variable named as angle. Note that it is not the variable that we have declared it here. It is the new way. You can change it here as you wish. And int angle, I'll read from the wire whatever the slave has sent, and I'll print them on LCD. Like I'll set the cursor here, then I'll print angle and then degrees, not Celsius, degrees. And when the master have done the wire dot request from, then when it is received on wire, when the slave receives the command from master that I want some information from you, it will do this event wire dot on request event, and this request event will do the thing like wire dot write, as it will write to wire the reading of this servo motor. Okay, the reading of the servo motor will be sent to SDA line to the master. Yeah, so that's it, the coding part. We'll see any error. Wire dot request from. Oh, I was spelling mistake. Oops. There is something wrong. Wire dot on request receive. Angle equal to wire dot read.
Yeah. My
Yeah.
in the other code you put slave address as one, the other one. Here you put just two.
Oh, okay, okay. Let it is printing. Okay. Oh, it is like. Yeah, okay. So you can see. Yeah, okay. So this was one of the project. So when I'll just explain you the code of this project. Slides. Yeah, so what actually is 7-segment LCD after this? A 7-segment LCD is just nothing but the array of 7 LEDs. Like they are connected all in like parallel with a common cathode or common anode, depending upon like what configuration you want to choose. I'll go with common anode. Like this A pin stands. Oh, sorry. A pin stands for this. Like the A is one. These are like this is one LED. This is one LED. These are like 7 LEDs, and it has like every pin A has one output. Like A will have 7, B will have 6, C will have 4, and DP will have 5. D will have 3. D will have 2. E will have 1. F will have 9, and G will have 10. So yeah, so this is like just array of 7 LEDs, and I'll go to the code here. You can check this project further. So actually, I have used a toggle switch also here. Also, you have received it in a task, I guess, a follow-up task in one of the session, I guess session 1. So with this, what I'm doing is I'll explain in the concept. I'll like do this is like basically a counter which can like count number from 0 to 99, and it get resetted after the 99 after 99 like this. With the values of toggle switch, I increment a variable I, which like these are like I use the switch. Before that, I use the switch cases. So if switch case based on the counter variable, this is like I have declared this a variable named counter, and based on the value of it, like suppose counter is 1 in the code now, so it will run this case and it will print 0. Else it will print as we press this button, this counter value is like incremented. I'll let you if you understand if you have made the toggle switch, then you will understand how you would have got idea that how to increment this counter value by 1. So this is what I have did to increase the counter value by 1, and after this, after increment, it will like go to from 0 to 1, 1 to 2, 2 to 3, 4, 5, 6, 7, 8, 9, 10. 10th case where it will print 9, and after this I'll again set the counter to 1 because I have to print 0 here, and I have to increment whatever LCD I have here, whatever like value, whatever uh, I have to increment this by 1. The 0 here must be incremented by 1. So with I2c protocol, I'll send the value of counter 2 to this Arduino. See, here I have to use I2c protocol because we are running out of pins here. Like it has 7 pins, but we have to use 1 pin for pull-up register. It is just like demo, and you can like increment. I have like send the counter value 2 after this becomes 0. The counter 2 is like incremented again and again. Like after this iteration, it will send counter value as 2, and it will run the second. It will run the next case further. Like it will go on doing. After it reaches 99, it will get resetted to 0. So yeah, you can look up on this code, and if you have any doubt, you can ask me in our group. And also we'll send a Google form where you can send your doubts. Yeah. So thank you guys for listening patiently. If you have any doubts, do ask it. We'll clear it as soon as possible. Yeah, I'll send the Tinkercad link where you will get code and both. Yeah, sure, we'll try doing that. Yeah, okay, so bye guys. Hope you enjoyed the session. Again, telling if you have any task, if you have any doubt, uh, you can ask and we'll give you a follow-up task, which will be like easy to do. You can do that to keep a hold on your concept we discussed today. Bye guys. Hope you enjoyed the session.
For my the attendance sheet and like save the recording also.